Editing a podcast usually involves hours of dragging clips, syncing audio, and keyframing text. We can replace that with a fully automated command line pipeline. We are aiming for an output exactly like this. It features crisp 4K text, cyan highlights that light up with the speaker, and glass-like UI cards sitting over a deep slate background. To achieve this without writing a single line of CSS, we will build a 4-phase pipeline. This hybrid approach uses Python for heavy data mapping and Node.js for the visual rendering. Before starting, you need 4 specific tools installed in your local development environment. Ensure you have Python, Node.js, FFmpeg, and the Faster Whisper library ready to execute. By orchestrating these specific tools locally, you remove the need for subscription-based editing software while retaining broadcast-level visual standards. Phase 1 begins with our raw audio. We use a Python script to initiate the first 2 stages of the data pipeline. First, the script feeds the raw audio file into Faster Whisper. This library transcribes the text and extracts millisecond-accurate timestamps for every single spoken word. With the timing data captured, the script runs semantic mapping. It scans the transcript for specific topics and matches those spoken sections to our corresponding diagnostic slides. All of this timing and mapping data is compiled into a single output, a manifest file called timeline.json. This JSON manifest is the absolute source of truth. It dictates a strict schedule for every visual cut and animation we will execute later. Locking down this precise audio data first prevents the timing and syncing errors that often occur during automated video generation. Now we move to Phase 3 and configure our AI agent prompt. We define a set of immutable design rules that the AI is required to follow. We start with the color palette. The prompt mandates deep slate backgrounds and vibrant cyan accents specifically for highlighted text. Next, we enforce a strict typography system. The AI must use geometric sans serif fonts, with headers set to heavyweights so they remain legible at high resolutions. Then, we define the animation physics. We explicitly ban all linear animations. Instead, the prompt forces the AI to use cubic Bezier transitions for every element entrance. Compare a constant speed animation on the left to an ease-out expo transition on the right. The right panel snaps quickly and decelerates fluidly. Applying glass-morphic attributes gives the right panel a drop shadow, a semi-transparent border, and heavily blurs the background directly behind it. Defining these specific tokens in the prompt ensures the AI produces a consistent visual identity without requiring manual code adjustments. With the prompt established, we execute the Phase 3 Node.js script to begin the rendering process. In the background, Node.js spins up the hidden canvas viewport. It takes the AI-generated code and processes it into visual frames natively at 4K resolution. Using the timestamps from Phase 1, the Node.js renderer ensures that individual words in our text light up exactly as the speaker says them. This split-screen composite displays diagnostic documents without cropping. We keep the document crisp in the foreground while filling the background with a darkened, blurred copy. Throughout this process, the Node.js script layers the USA Visible Podcast watermark over the background. If the AI uses a default browser font or a linear animation, an automated quality gate crashes the render, forcing the script to autocorrect the code. Rendering these graphics natively at 4K ensures that text and vector elements retain maximum crispness before the final assembly. In Phase 4, we use a final Node.js script to orchestrate the stitching of our visual frames and audio assets. Avoid using the standard -shortest flag in FFmpeg to end the video. This shortcut often results in audio desynchronization. Instead, use the ffprobe tool to measure the exact durations of your tracks. This allows you to explicitly enforce perfectly matching endpoints for both audio and video. For the final encode, use these parameters: libx264, a very fast preset, and a constant rate factor of 18. Sending commands directly to FFmpeg ensures the assets are assembled with no quality loss, and the timing remains exactly as specified in the manifest. When you open the final MP4 file, the physical result of the automation is immediate. You have a high-resolution video that required no manual editing. The cubic Bezier animations snap smoothly, the deep background blurs add professional depth, and the text highlights line up precisely with the audio, all without a single manual keyframe. You can adapt this pipeline for other projects by changing the hex codes in the CLI prompt to match your specific brand colors. If you want to run this setup on your own machine, check the video description to download the base prompt template. Mastering this orchestration pipeline allows a standard laptop to execute the entire high-end production cycle automatically.